Hello, Math 1093. This is Dr. P with Action and Reaction. In this video, I want to talk about the fact that exponential functions and logarithm functions are inverses of each other. So first of all, let me set up that function machine picture that we've been talking about that shows an exponential function. Okay, so let's say this function is f of x equals 2 to the x, just as an example. And then the inverse function of that is going to be g of x equals log base 2 of x. So we talked about how these two functions, 2 to the x and log base 2 of x, are inverses of each other. These are inverse functions, that is. And remember, the main idea behind inverse functions is that they switch inputs and outputs. So if the input to this function, 2 to the x, is some number like 3, which is an exponent, then the output, in this case 8, that is a power. It is the third power of 2. Okay, so exponential functions take in exponents and give you powers. All right, you always love something that gives you power. All right, anyway, inverse function, log base 2 of x, does the reverse of that. It takes in a power, like 8, and spits out an exponent. So anytime I write down an expression like log base 2 of 8, and I say that's equal to 3, I should think of this as an exponent. A logarithm is literally an exponent. Okay, now there's something else that I can do with this idea of inverse functions, the idea that logarithms and exponentials are inverse functions of each other. That is, I can see what happens if I compose them and then run these two functions in order, in succession. So let's say I have a function like f of x equals 2 to the x, and then I compose that with the function g of x equals log base 2 of x. So let's see what happens if I start with some number. I don't know, let's say, let's pick 5. Okay, so that's going to be an exponent. Whatever I input into an exponential function is an exponent. Well, out comes the number 32, which is a power. It is a power of 2. And if I feed that into the log base 2 of x, the logarithm function, what comes out? Well, what comes out is going to be an exponent. And it's going to be the exponent that makes 32 when you raise 2 to it. Well, that is the number 5. Okay, so this function here, the inverse function, it undoes what the exponential function does. So in other words, if I were to run these two functions in order, what is it I'm really doing here? I'm taking 5. And then I'm raising 2 to that power, and I'm taking that number, and I'm taking the log base 2 of it. And it turns out that's 5. And that's actually a general principle. There's nothing special about 2 and 5 in that scenario. Anytime I take a logarithm base b of b to the x, what I get back is x, because this function here is turning that x, which is an exponent, into a power of b. And then this logarithm function is taking that power and turning it back into an exponent. All right, so this is actually a general rule about how logarithms interact with exponentials. And what's even better is you can also compose things the other way. So I could write down the logarithm base b of some number. I'll call this one y. And then say, what is b to that power? Well, now I'm saying, okay, let's take y, which is a power, because the input to a logarithm function is a power of something, power of b. So I'm taking that power, turning it into an exponent, that's what this is, and then I'm saying let's take that exponent and run it through this exponential function. That gives me back a power. So b to the log base b of y is equal to y, because what this really is here, just want to put a finer point on this, what this is the exponent that you raise b to in order to get y. That's the definition of this. So if I raise b to it, to this thing, then I should get y. That is the kind of argument that turns your brain into linguini. You really have to think about it a few times in order to get the gist of it. But these are two very important rules. I call them the inverse function properties of logs. Inverse function properties of logarithms. Okay, and now we're going to use these to solve a problem. So let's come over here. I've given us a problem to work on. I've asked us to solve the equation e to the 3x plus 4 equals 10. Now, by the way, what is e? I'm not sure I've mentioned this before, but e is a special number in mathematics. Its value is approximately 2.718, and it has some special properties which I'm not going to talk about in this video because it would take us a little bit far afield. Well, I'll talk about one of them. One way of getting e is to add up an infinite series of numbers. It is this series, and then this continues on forever. Okay. Now, by the way, you may be thinking I'm dividing by 0, but actually 0 factorial is defined to be 1. So really the series is 1 plus another 1 plus 1/2. These are factorials. 3 factorial is 6 plus 1/6. And why we would pick that series, or why there would be anything particularly special about it, it's just going to have to be a mystery for right now. I'll try and say a bit about it later. But just for now, take my word for it that e is a very special number in mathematics, and it's especially nice when we're doing calculus. That's why we worry about it at all, is that this is a pre-calculus class, and e is the exponential base that happens to be used the most in calculus, because it just works out a little bit more elegantly than the other bases. More on that in a semester or so. Anyway, we've been tasked with solving the equation e to the 3x plus 4 equals 10. Now, sometimes when we see an exponential equation, the trick, or I should say the best strategy, is to turn everything into the same base. Turn everything in this equation into something that has the same base. So maybe turn both of these things into something with a base of e. Now that's tricky here. It is possible to do that with 10, but a little bit tricky to figure out how. So I'm going to suggest a different strategy here. I have an equation where I've got e to the 3x plus 4 equals 10. And I would just love it if I could isolate this x and get it out of the exponential. Okay? Well, now I have these inverse function properties, and they give me a way of unpacking an exponential. If I have an exponential, then I can get rid of it by applying a logarithm to it, the logarithm with the same base. So I'm going to try and do that. Now, the logarithm base anything is a function, and I can apply it to each side of this equation as long as the logarithm is defined. And the logarithm of 10 will be defined because 10 is a positive number. So what I need to do is just apply the same function to both sides. I mean, I can't just go changing one side and not change the other. I've got to do the same thing to both sides. So I'm going to apply the logarithm base e, there we go, to e to the 3x plus 4, and also apply it to 10. Okay, now you may know from your prior studies that logarithm base e has a special name. It is called the natural logarithm. That's what it's called on your calculator. And that's important because we are going to absolutely use a calculator to solve this thing. Okay, so just a note, ln means logarithm base e. That's a definition. So now we have the natural log of e to the 3x plus 4 equals the natural log of 10. Well, the natural log of e to anything is whatever that thing is. It's 3x plus 4. And that's because the natural log function undoes whatever this exponential function base e does. All right, so 3x plus 4 is equal to the natural log of 10, whatever that is, but this is a number, and I can find it using my calculator. Okay. In fact, what I'm going to do, though, is I'm going to leave this as natural log of 10 throughout this process, and then I'll evaluate it at the end of the process. Okay. So if I want to figure out what x is, at this point we're just solving a linear equation. It's just that the linear equation has this funny, somewhat unknown or mysterious number at the end of it. But the idea is still the same. I'll subtract 4 from both sides, get 3x equals natural log of 10 minus 4, and then divide both sides by 3. Now when dividing both sides by 3, remember I have to divide the entire right side by 3. Can't just divide one of those terms. I got to divide the entire right side by 3. And now I have x equals natural log of 10 minus 4 all over 3. And if you wanted a solution to this equation, this is actually it. I mean, I could just say x equals natural log of 10 minus 4 over 3, and that's a perfectly fine answer. But if you want to know about how much that is, you can use a calculator. So I'm going to use a calculator, type in natural log of 10 minus 4 all over 3, and I get negative 0.566 approximately, negative 0.566. So I'll say x is approximately negative 0.566. and that's an approximate numerical solution to this equation. So anyway, major point of this video is that these properties, these inverse function properties, that logs and exponentials cancel each other out in either order, this order, that is exponential then log, or log then exponential, either way they cancel each other out. And this is a super useful strategy for solving equations that involve exponentials. All right, so that's it for this video.